Okay, so we've got here another circuit that we're going to look at, and this is the other example or assessment problem. Now this looks like a very complicated circuit, but I want to do this one because it is a complicated circuit, but you just have to kind of take things one step at a time. So problem states that this switch here, I'll go ahead and label these. I believe they called this switch A and this switch B. Switch A has been open for a long time and switch B has been closed for a long time. And then so basically they're wanting to know what happens here with this. Now, as far as like what's the, you know, words escaping my mouth here, what's the equation for this circuit here? So, because then at t equals 0, this switch closes here, and then at t equals 1, this one opens, and so does this one. Alright, now let's first talk about what happens with this switch being closed here. So first off, this part of the circuit's not even there. Well, I'm circling it in air here, so I didn't even know if it saying it. I'll kind of box it off. This part of the circuit here is not even present for t less than 0, because that switch is open. So what do we have left then? Well, let's go ahead and draw what we have left, because we need to figure out what the current is initially. And I didn't leave myself enough room, so what I'm going to do is lasso this. Let's try lassoing it again. Moving it down. Because the switch is closed, that's what we have. And my inductor almost looks like a resistor there. And some of my resistors look like inductors. That's why I label everything again, so I know which ones are inductors and which ones are resistors. Now, this is the circuit for t less than 0. Now we have to think about this for a second here, and what we have to think about is the effect of this wire here, because this wire is shorting out. So basically current's always going to take the path of least resistance. So if I just even follow this here, current's coming up here, and if current had a choice to go down here, it would encounter some resistance, either like the 9 ohm resistor or the 6 ohm, or it could go up here where there's 0 ohms resistance. And because there's 0 ohm resistance going up, and I don't know if you actually are saying that, so let me draw it down. If current were trying to go down here, again, it would encounter either a 6 ohm or a 9 ohm resistor. But if current goes up this way, it encounters 0 ohms. And so actually, this 8 amp current source is just going to do this with that short. Basically, you're shorting out the current source. And so what that's telling me is no current is getting down into this part of the circuit. So if there's no current getting down into this part of the circuit, that means we must have that this current I here, I at 0 minus, is 0 amps, because there's no current getting down into there. Then I at 0 plus, because current stays the same for an inductor, is 0 amps. Now we need to look at this with the first switch closing. So then when it closes, I'm going to do a lasso to copy this back down again. So we'll do a copy, and then a paste. Maybe we'll do a paste, come on. There we go. So I'm going to modify this circuit a tiny bit. First off, I'm going to erase some of these blue dotted lines that I had. And I erased this, and this is a 10 volt. And then what I'm going to do is I'm going to erase the switches here because we're going to write what state they are. So this is a wire here now, and this is still a wire. And this is for t between 0 and 1. This is the circuit I have. So now we need to figure out what the final current is. So the final current, again, would be, this would act as a short. So we need to figure out what current is going down here. Now, remember, this current is still being shorted out here. This current source is still being shorted out, so that's essentially not there. But we have to be a little bit careful here in doing this because basically we have this 8 ohm resistor here, and it's going to be the current through this 8 ohm resistor. So let's see if we can redraw this a little bit here. We have to be careful because I don't want to mess up any connections here. So what we'd have here, 10 volt. You know, actually what we're going to do here, there's a lot of ways we could do this. I'm going to do a source transformation. So this 10 volts is going to become 2 ohm with a current source here. And that current source is going to be 10 volts divided by 2 ohms, which is 5 amps. Then I've got a 2 and 3 ohm resistor in parallel. So I'm going to do 2 in parallel with 3, which is 2 times 3 over 2 plus 3. So this would be 6 over 5, which is 1.2 ohms. So I'm going to just keep erasing and redrawing on this circuit diagram here. So then what do I have here? That means this is now just a single resistor of 1.2 ohms. Then I'm going to do another source transformation, and I'll write this here in red now. So the source transformation I'm going to do, I'm going to have 5 amps times 1.2 ohms, which, let me do that on my calculator so I don't make a mistake. That gets me 6 amps. I'm sorry, not 6 amps, 6 volts. So let's draw that. So this is now gone. And now I've got a voltage source here of 6 volts. Now, on an exam or a homework, I would recommend like redrawing the circuit as opposed to doing what I'm doing, because I need to be able to follow your work. If I can't follow your work, you know, I might not give you full credit for the problem. So 1.2 ohms. But then what do we have? We have 1.2 ohms in series, which in series just means we add with a 0.8 ohm, which gets me adding 2 ohms. Alright, so I'm going to erase this now. Two ohms. And then I'm going to do one more source transformation. I'll write this one in blue. 6 volts divided by 2 ohms, which is 3 amps. And so now I've got this 2 ohm resistor and a current source of 3 amps. Now, after doing all those source transformations, life has become much easier for me. Because, again, think about current here. Current's always going to take the path of least resistance. Well, it's going to go up here, and it's going to go down here, and it's going to say, okay, there's a 2 ohm resistor. Maybe I'll go down there. It's going to come down here, and it's going to say, wait, there's a wire here. I'm just going to go down the wire, because it's always the current. All of the current will always go down if there's just a wire there. So this is the path of the current here. So what that means here is my final value is equal to 3 amps. So let's kind of backtrack where we're at in this problem here, because we're still just doing this for 0 to 1 second so far. Is what we've gotten here is we've gotten for t less than 0, this is my circuit, and we saw that all the current was going here, so my initial current is 0 amps. Then we did it with the switch closed and said, okay, well, the inductor is going to behave as a wire when it's closed for a long time. And then this is going, we did a bunch of source transformations to get that the final current through the inductor would be 3 amps. Okay, so now what we have to do here is we have to actually figure out what my tau is. Now, tau is actually probably the most complicated problem we've done to find tau. So I'm going to go back and, well, actually I've got it already in the clipboard. I'm going to paste that circuit again, and then redraw some things here. Okay, so then we know that this is a straight line, and then this here is also a straight line. Alright, now we have to find our equivalent looking from inductor. So remember, if we have voltage and current supplies, we have to turn them off to find our equivalent. And remember, a voltage source becomes a wire, and a current source becomes an open circuit. So I'm going to position this a little bit here. I'm going to move this resistor over here, 2 ohms, and then we're going to go ahead and I'm going to just again kind of redraw the circuit and erase it here. The reason I do that is because I don't have a ton of room to redraw the circuits on this screen here. So we again have 2 ohms in parallel with 3 ohms, which we've already done that computation. We get 1.2 ohms. So I'm going to draw that here, 1.2 ohms, and then we have the 1.2 in series with this 0.8. So that would be just 2 ohms. And so I've got a 2 ohm right here. Now let's take a look at the other side, because this 2 ohms is now in parallel with that 2 Henry. If we look at this other side, first off, notice that there's a wire here shorting out the 9 ohm resistor. So that is not even there, and I'll draw this here. So we have this. But then we have it's like, what's going on here? I needed to erase 9 ohm. We then have a 3 ohm in parallel with 6 ohm, which is 3 times 6 over 3 plus 6, which is 2 ohms. So this is now just a single resistor. That's 2 ohms. But now we can clearly see here our equivalent is going to be 2 ohms in parallel with 2 ohms, which we know when they're the same resistor value we get 1 ohm. So then that means my tau is simply 2 henries times 1 ohm, which would be 2 seconds. So it's a big value for tau. So that means for part A of this that my current is equal to, well, it's my final value plus my initial value, which is 0, minus my final value, e to the negative t over tau. which tau in this case is just 2 seconds. And since it's seconds, I'm not going to bother writing the seconds down. We always write the milliseconds down because we're emphasizing it's milliseconds, and we have to make sure units are the same when we plug things in. And so my current here is 3 plus, or not plus, 3 minus 3 e to the negative t over 2 amps. Alright, so a lot of work just for the first part here. We now need to do part B, which is finding the current for t greater than 1 second. So I'm going to paste the circuit down again. And redraw some of things here. Whoops. Okay, so at t equals 1, the switch there is back open. And this switch is open as well. So we're going to have a much circuit that's a lot simpler than what we've had in the past here. So before we dive into any of this here, we're going to first off figure out what my I at 1 minus is. And we do that again by simply plugging into the equation here, 3 minus 3 e to the negative 1 over 2 amps, which if we do this computation, I'm going to do it real quickly on my calculator here. We get 1.18 amps. So that means I at 1 plus is 1.18 amps. So we have my initial value here. Now let's draw this circuit here without all the extra bits here. So because we have this now where some of those switches are open, so what I'm left with is the following. Alright, so this is the circuit I have right now. Now, you could probably do some source transformations to actually figure out what the current is here, the final current. Because remember, this is going to be just a wire here. Because when it's on for a long time, it's just going to be a wire there. And actually, we can go ahead and figure this out probably without having to do anything super fancy because, well, what do we have here? This wire is going to short out that 3 ohm resistor. So really what I have here is, let me draw it over here. I've got that wire that short out that 3 ohm resistor. This 9 ohm, 6 ohm, and then 8 amps, 9 ohm, 6 ohm, and then the current here, that's I. That's what I'm looking for. Now, honestly, what I'd probably do here, as I said, you could probably do a source transformation and figure out the current that way. In fact, I'm sure you can. I'm just going to do a loop, though. I'm going to write a loop equation here because I have 2 loops, but I already know what one loop is. So I have this is I1 and this is I2. But I know that I2 here is simply 8 amps. And then if I write a loop equation for I1, wow, 2 amps, and I wrote 8 amps, and I did not write 8 down. Okay, so 8 amps is I2. So then I loop 1 here Well, I'd have 6I1 plus 9, and it would be I1. And let's see here, are they going in the same direction or opposite directions? Well, this one's going this direction here, and the I2, so they're going in the same direction, so plus 8 is equal to 0. So we would get 15I1 equals negative 72. And you would get then that I1, which is equal to I final, negative 4.8 amps. I wrote volts there, but this is current, so this is amps. So as I said, you could easily do a source transformation to get that correct as well, but I went ahead and just did a loop there. Alright, so last thing we need is we need to get tau here. So I'm going to lasso a circuit here again, copy and paste it. Okay, so I need to clean up this diagram a little bit here. Alright, so now I still need, I have my, let's get back here. I have my initial current, my I0 is equal to, well, what was it equal to? Let me scroll back up here, 1.18. I have my I final is equal to negative 4.8. So what do I have left to find? I need to find my tau. And again, I have to find R equivalent. So if I have this here, again, we turn off the power supplies, which means this 8 ohm becomes an open, so it just kind of disappears. And then we can see, what do we have here? Well, we've got 9 in series with a 6, so that's 15 ohms. And I'll go ahead and redraw what we have here. So this is 15 ohms. And then we clearly have a 3 ohm in parallel with a 15 ohm, which is 3 times 15 over 18, which is 2.5 ohms. So my R equivalent is 2.5 ohms. And then I can simply figure out what tau is, because tau is just equal to L over R. So tau is, well, my L is 2 henries divided by sorry, I'm spaced there for a second, divided by 2.5. Which is 800 milliseconds. Alright, so now we're ready to write my equation down. So my current, and this is for t greater than or equal to 1, is going to be my final value, which is negative 4.8, plus my initial value, 1.18, minus the final value, e to the negative t over 800 milliseconds. And I did it again. It's minus parenthesis t minus 1 divided by 800 milliseconds. I even told myself at the beginning of the problem, don't do the same mistake, and of course I did the same thing again. Which then we simplify this out just the tiniest bit here, and you get negative 4.8 plus 5.98 E, and then again if you divide by the 800 milliseconds you would get negative 1.25, and then t minus 1. So these two problems that we did today, as I said, I think these are probably the most difficult ones with the switches here. So quite frankly, as I said, if you can understand how to do these problems, you should be able to understand any of the problems. Okay.